I come from the NEC Labs research labs in Germany. And I'll be presenting ClickOS, and this is work done by me and my folks at NEC, as well as some other people at the University of Bucharest. So in one sentence, ClickOS is a VM to do network processing. So what's the motivation behind it? A long time ago, some folks designed the internet, and how does it look like as we are taught in schools? End hosts with a network in between containing switches and routers. Pretty simple. But in reality, middle boxes are commonplace in today's networks. They are very useful for a high number of reasons, and they extend operators' network for a lot of features. Security, such as firewalls, intrusion detection systems. Monitoring, such as DPI boxes. Load balancers, dealing with the address exhaustion issues. Performance, such as media gateways, transcoders, YDR accelerators, and some others of a more dubious nature, like the advertisement insertion box over there. I mean, I'm having some issues with the display port, so you cannot see exactly how this would look like, but these middle boxes are really useful, but there are a lot of disadvantages at the same time. First of all, they are really, really expensive. One of the boxes I showed you, like the media gateway, costs around 200K. It's really difficult to add new features. Often you get locked in to vendors to upgrade your firmware, add new features, and so on and so forth. They are difficult to manage. It often requires specialized personnel to manage the box. Normally you deploy these boxes to keep with the peak rate, so they cannot be scaled, like you add more like you want. And it's difficult to share these devices among other parties. And since it's a hardware market, it's hard to new players come along. It's hardware. So clearly, if we had some way to virtualize these middle boxes or shift these middle boxes to be software instead of expensive boxes, we would have, we mostly would solve most of these issues we have here. But it is still not clear if we can do it in software and really coping with the performance that the hardware middle boxes can achieve. So we believe so, and that's what I'm talking about here today, and that's what we propose with ClickOS. ClickOS is a mini-OS-based Zen virtual machine that runs on top, that runs Click modular router. So let me first talk to you a little bit about Click. Click is a framework to design routers and process packets, and has this concept of elements. Each of these elements does an operation to the packets or receive packets. For example, the configuration on the side basically decreases TTL and forwards back the packet to a different interface. These elements are contained in a configuration, and basically you install it either as a user space application or as a kernel module. These elements are exposed, they're counters, if we have a counter on an interface, for example, via variables on the /proc file system. And for example, the counter, you have a count element to just a read-only, and to reset the counter, you just write 1, for example. For ClickOS, we compile 262 of these elements, excluding the ones that deal with the file system. And if you want to further extend the Click, you can just write new elements. It's quite easy. So an example of a Click configuration looks something like that. You have from netfront to receive packets and to netfront to send packets out. You have an IP filter element that allows packets from 10.01 and destination 10.101, UDP packets. Otherwise, drops it all. So you can see that it's quite easy just to filter packets, for example. So what's ClickOS? Typically, we have in Zen Our per-virtualized operating system is slightly modified, working on top of Zen, and the kernel and the applications running on top. In the case of ClickOS, we use MiniOS as our guest operating system, and we just run Click, and we call the whole thing ClickOS. So it kind of follows the trend of OS3 in the previous presentation, or Erlang on Zen, Mirage, so that it's application-specific operating systems. So the work we did was having a build system to build kind of these mini-OS apps that we use to build ClickOS, and what we get is a 5 megabytes image in total, in size. And we had to emulate the control plane, so we don't have a /proc file system between VMs, so we had to emulate this over Zen via the Zen store. And we further reduced boot times as well. We started with something like 1 second, and we get it down to 30 milliseconds boot time. And the most important of the contributions are actually driving 10 gigabits for all packets, for almost all packet sizes. So in these VMs, what matters is not bandwidth, but the ability to process really, really high packet rates. The talk will be focused on this last bullet point, but let me just give you one slide of what consists the tool chain and the tool stack. We'll compile a new lib, which is slightly modest libc. It's normally used for embedded systems, and it's already quite old, that version. And we compiled as well LWIP as our networking stack and some other utilities in order to compile Click to MiniOS. We also use this toolchain to build, for example, iPerf and the fast packet generator based on NetMap called PacketGen. We expect to actually port other applications on top of it. Our tool stack is based, we have our own tool stack. We don't use XCP, Excel, or SAPI on Zen. We design our own Cosmos tool stack, which is basically using the Zen libraries, and we use Swig to generate the bindings for our tool stack. For now, we support Python, JavaScript, and OCaml. It just compiles for now. The optimizations were, okay, it was not exactly optimization, it was like a learning process. But most of the contributions of having slow boot times were preferring OZenStore did, the new OZenStore implementation shipped in 4.2, if I'm not wrong. A different network attach. The hot plug scripts really slow things down, like 200 milliseconds. And further booting uncompressed image as opposed to gzipped image. Actually, uncompressing the image takes longer than booting the VM itself. So that's it for the control plane. For this talk is about how we actually improve this. And our main objective is to drive these packet rates. So 14.88 million packets per second for minimum-sized packets. For reference, a TCP hack is a minimum-sized packet. For bigger-sized packets, 810,000 packets per second. So we did the performance analysis of this, the whole pipe. And normally we have our network driver attached to an Open vSwitch or Linux bridge, and a VIF for each VM, which is managed by NetBack. Then we have the shared memory used with the ZenRing API in event channels to exchange notifications, our NetFront, and our Click environment. Additionally, we had two elements, so for our network interface, which is NetFront, and so that's the configurations character for packets and so on. So when we plug all of this together, there were several bottlenecks. First, the Linux bridge, just a disclaimer, numbers change all the time, so these are actually a bit better in Open vSwitch, but a long time ago when we did this analysis and started working on improvements, it was something like this. For For maximum size packets, it was able to forward more than 300,000 packets per second. When we place netback in 350, and with the whole thing together, just roughly 225,000 packets per second, which corresponds to 2 to 3 gigs of throughput. So there are a lot of issues on this pipe. And first of them all is the bridge that we use. Afterwards, it relies on TCP, the Linux host stack, which is not exactly, it drives 10 gigs, but not exactly with really high packet rates. Copying, each time you want to send a packet, you copy that, you need to copy the page to the backend domain, and this copy, although it's done in batches, is really, really expensive. Relying on SK buffs, it uses the Linux stack, so the allocation and manipulation of these socket buffers are really expensive. And also, MiniOS backend and front-end driver is not exactly as mature as Linux. It's pretty functional, so it's also slow. Roughly 2 times less performance than Linux. And RX was a mere like 100 megabits of performance when we get it. So as starters, we started not killing the whole the backend and front end, and start doing small optimizations on the backend driver. And we started by replacing the switch called Vale. I will talk a bit Vale and NetMap right after. We did slight modifications to ZenNetback to support multi-page rings. This is work basically ported to NetBack, but it's work from Wayne Liu. And because we are relying on Vale, it doesn't use SKBs. We removed that packet metadata manipulation. And overall, the results were actually nice, pretty nice. We get 3 times better performance and 1.2 million packets per second for minimum size packets. So before telling the very last piece, let me give you just a background on NetMap. NetMap, available in FreeBSD and Linux as a out-of-the-tree build, is a fast packet I/O framework that drives line rate for 9 megahertz CPU, down clock to 9 megahertz. It roughly corresponds to 67 nanoseconds per packet to fill up the 10 gigabit with minimum size packets. It requires changes on the device driver, but these are minimal changes just to support the NetMap mode. But all the NIC registers and physical memory addresses and the packet descriptors are not exposed to user space in any way. These must be validated by the kernel when you poll for packets and thus not accessed by user space. It's similar to what NetChannel on the previous presentation, where you map the software ring into user space and you use those data structures, copy packets, and basically poll and flushes out, bypassing the Linux host stack. Vale, on the other side, was born like a small extension to NetMap, and it's a software switch that drives between virtual ports, around 18 million packets per second. Lately, in the latest release, like 22 million packets per second. The graph on top shows a comparison of all the 3 switches, the FreeBSD bridge, OpenVSwitch, and Vale. But just a small detail. The Vale case is between virtual ports, whereas the OpenVSwitch and bridge are between 2 NICs. So we did a number of extensions to Vale to let us attach NICs to the switch, to modularize the switch, which means you could implement your own switching function, and having your own modules that extends the switch. And basically, the way you use the switch is like a normal NetMap API, not normal application using NetMap API. So plugging in all of this together, we got rid of the netback and netfront, and we implemented one of our own, whereas it's a really small netback that tries to mimic what the kernel does to the application. We remove the extra copy, which means the buffers are granted to the VM. The ring protocol is not the same as in Zen. Like you have a request and expect an IO response. You copy packets to the ring, notify the backend, and you forget. Event channels are used to proxy the poll. So when you send a packet, you need to poll in the user space. You need to poll the ring to send the packets out. And in this case, we emulate this with event channels. But the biggest problem with this is that we break Linux and other front ends. But to show that these optimizations are viable, we also implemented Linux as a compliant front end. We eliminate the copy, so I thought it would be good to mention how much memory do we share. Netmap buffers are allocated in contiguous pages, and buffers are around 2K. So, which means for the normal ring size of Netmap, which is 1024, you share a total of 2 megabytes per ring as of Netmap API version 3. We provide different ring sizes as a form of, depending on the throughput our ClickOS VM or Linux requires, you require a smaller batch. So basically, the way Netmap works, you basically issue IOCTL to open the Netmap device. You open the Netmap device and you do an IOCTL to register the interface to Netmap, which detaches the Linux from the Linux host stack. Then our backend will grant the front end the ring and the buffers, including the grant references of the buffers inside the ring slots. The front end on the other side grabs the grants regarding the ring and checks reads the slots in order to map the rest of the buffers. So to run our ClickOS VM, the minimum memory requirement is for 64 ring slots. It's 6 megabytes in total, and we drive 10 gigs for with this ring size as well. So let me just show you some performance evaluation of our system. I told you that our VMs boot in 30 milliseconds, and this is when we boot 400, how does the boot times evolve? So you ask yourselves why we want 300 milliseconds boot time. The main motivation is that you are able to react as the traffic reach a peak, and you can expand the number of virtual machines in other machines in order to cope with higher rates. When I say higher rates, like 10, 20, 30, 40 gigs, for example. So the time to create a VM evolves from 22 milliseconds up to 220 milliseconds. The time to instantiate click configuration takes around between 5 to 20 milliseconds. Regarding the packet performance, we got a huge improvements, and we basically achieve around 9 million packets per second for receive side, and for TX, we achieve 1438 million packets per second, which is 95% of line rate for medium-sized packets. This, although, has changed a little bit on the latest Netmap API version, which we are down to 11.12. And you can see that as we decrease the ring size, we decrease the throughput as expected. The cost of event channel starts to be a bit more visible. But as you can see, all the other packet sizes, we fill up the pipe. This was tested on a low-end server of 4 cores at 3.2 gigahertz with dual port 10 gigabit NICs. Each core is assigned one CPU core for the VM, the rest for DOM0. So after getting 10 gigs, we asked ourselves how we would scale for more NICs. So we actually ran some experiments to see if we were able to drive 40 and up to 80 gigs of throughput. And we actually did. So the bars are TX only, just VMs doing a packet generation. And the lines represent forwarding. So VMs actually processing packets and forwarding back to the outside world. And we achieved roughly 30 gigs, 30 gigs for 3 ports. And this is only the rate you receive, so remind that it fits full duplex. It's the double of the performance, roughly. So if we manage TX with RX, it's actually 60 gigs, around that. And we don't exactly scale that well for minimum size packets over multiple NICs. Again, this was on the same setup as the previous experiment. We assigned 3 cores for DOM 0 and 3 cores for the VMs. Each of the cores has one NIC, all the NIC interrupts assigned to it. Otherwise the NIC starts to starve and they're not able to process all the packets. So there was a bit fine-grained tuning on the interrupts. So the Linux guest performance also gained some huge improvements, but a disclaimer, this is not exactly a fair comparison. So the highest of the bars are the highest bars are using NetMap API, which Xen and KVM don't support it, and you still get all the bottlenecks of the host TCP/IP host stack. So this is actually my favorite graph, is when we actually run middle boxes on ClickOS. So the first one is just packet forwarding. So it doesn't touch the packet. The second group of bars is an Ethernet mirror. Basically, it changes source and destination MAC address, forwards back the packet. The third one is a standards compliant IP router. The fourth is a firewall loaded with 10 rules. The carrier grade NAT, which has, I think, 10 flows with randomized ports. Software BRAS, which for those who don't know, it's the first hop of the DSL subscriber. And it does the PPP termination, PPPoE termination, IP LCP handling, and session management as well. A load balancer, a flow monitor that gathers statistics about the flow, and intrusion detection system, just checking the contents of the packet with just 5 rules. After that, since this is a middle box, it's not a hand system, it's actually important to have really low delay. And our ClickOS machines add just 40 microseconds of delay to the whole traffic. And we compared with other systems, and we almost cope with DOM 0's delay. And we did the best of our efforts to put the KVM setup the lowest possible. And we got also huge improvement compared to the Linux DOM delay. So this is ClickOS, a really tiny virtual machine to do packet processing. We drive 10 gigs. I will show you a demo just right after the presentation. I will be at the Xen booth tomorrow between 10 and 11. So feel free to go there, and I ask any questions. I will show you more demos. And in the future work, we are exploring the performance on NUMA systems, which is not exactly that good. Doing high consolidation of these VMs, something like running 1,000, 2,000, 3,000 VMs. We did some experiments and already are 2K VMs on a single machine. and doing service chaining of these virtual machines, like chaining these network functions with each other to do more packet operations. Last and not least, in the Zen Summit, we told that we would be open source, but we weren't clear how it would take. There is a presentation on an SDI 2014 about ClickOS, and we'll be open sourcing on that time, which is April 4th. And that comprises patches to MiniOS, RF requests for comments on the backend and frontend drivers, and more things to come. So that's it. Hope you guys like it. Any questions? Yeah.
You had a picture with the queue from different Ethernets and so on. Second picture in this presentation, I think. And you had stuff like paint.
Yeah.
And TTL. What is it?
The configuration is pretty simple. It just decreases the TTL on the ICMP request. Just that. It's just to visualize how the configuration works. Just decreases TTL and forwards back the packet out.
Paint?
Paint is just a click internal thing to mark the packet if you see it said again.
Like internal processing.
Yeah. Not actually something on the packet. Yeah.
So it's like a switch jargon? Or
Sorry?
it's like a jargon for this?
Yeah. Oh. Okay. Yeah. He was asking that what the configuration does, the TTL, and what paint means on click. Excuse me? Yeah. This is for just one VM. Yeah. Yeah.
The modifications that you make to send, for example, the switch, how hard it is for someone to actually run that, take it and put it into normal SAN information? You have to, you plan on patching SAN, or it's going to be how, from a practical point of view, how can you start using?
Actually, right now, it's on FreeBSD 10. It's already in FreeBSD 10. Yeah, exactly. So NetMap is normally refers to NICs. Vale is a switch, so they kind of work together and they use the same API. So the API is really quite simple. If you go to, so this is from Luigi Rizzo, and we made some contributions which are already on FreeBSD 10. So you can attach a NIC, you can attach the host stack, you can extend the switch with your own switching functions, and all of that is already in FreeBSD 10. Any more questions? Okay. Oh. Yeah. The rates I'm showing here. So for example, the middle boxes. It's actually, for example, that setup. So the middle boxes on the Zen machine, one of them, and 2 end hosts with normal TCP, Linux stacks and all that. Sorry? Yeah. So, I'm not sure if I still have 9 minutes, and I would like to show you a demo. So this demo, the resolution is not exactly quite good, but this is just to show how the boot times, and So basically, you have the create VM over there, and Cosmos is very similar to Excel, for example. And basically, you create the VM over here, and we start the click configuration. And let's see how it does. Basically, we boot 100 VMs. Now, on the other machine, they are connected back to back. We just ping the VMs to see if they're actually working. So it's an R ping, so it goes to every single VM, and every single VM runs the same configuration, answers to the same ping. So that's it. There are more demos, like on-demand, 10 gigs, seeing an HTTP transfer with a VM booting on demand, and can see all of that. Just go to the booth. I'll be there at lunchtime in 10 to 11. Thank you.
Excuse me, your name is João?
João Martins.
Ah, okay. How?
João. It's Portuguese, a bit difficult.
I see. So, unrelated question. I had before an IoT, and they had like glass, and they had this glass. You know what glass? No. This one is this one. Yeah. So what is this one?
Βοήθεια, έχεις περάσει στις μπύρες σου.
I'm not exactly but this one is so software mirrors are the one that doesn't give you this one I think is already like for 6 weeks.
Okay, sound check. Okay, you need that? No, you put it on when you speak in. I'll go up. And you say something, right?
And what do you want to
And then,
say?
and then if it's
Doesn't matter.
whatever,
In whatever language you prefer, it doesn't matter.
and whatever, and then if it's if I say if I do that, it's fine. And then if not, you may have to adjust the microphone or something.
Okay.
And what resolution are you on your laptop?
I think I configured it. Yeah, I configured it already. Wait a second. That's
Σε εργασία μου βάζει χαλαρό πεντάρι.
Yeah, thank you. Great talk.
okay. No problem. What do I need to do?
Yeah, just talk it. I go up.
Okay. Start talking. What do I need? Take finger to short the slides.
Τώρα δεν σου λέω να κάνω
Perfect.
normalization.
Yeah. Yeah. Finally.
But actually,
Σωμήμα. שומעים אותי אם אני מדבר פה? אני לא חושב.
I was just wondering what would happen if we serialize all these VMs. What would happen to performance? Would it
you had 3 in this performance.
ככה, אין לי בעיה. נשאר ככה, פחות מלחיץ. בשנייה האחרונה נכנסים... אוקיי. על מה עשית? על מה עשית פה את וואו, זה התגליות. Just tell me when to start.
3 more minutes?
3 more minutes. If you want, you can start early, but
Yeah.
but then you have people just coming in
Okay.
when you start. I do the timing for you as well, so if you occasionally look up, I kind of give you 10 minutes and
Yeah.
5.
Okay.
Yeah.
I have a clock.
Oh, you have a clock, perfect.
שתי דקות.
And make sure you repeat the questions such that when people start
Okay.
comments will be out of context.
Κολλέρα και τέτοιο. Μόνο πυρετώνα.
Okay. Can you hear me? Yeah. Okay, I want to start. Hi, my name is Gilad. I work for Red Hat. I'm a co-maintainer in the Overt project, and I'm working for the SLA and scheduling team. Today I'm going to talk about VM scheduling within Overt, how it got evolved, and etc. Basically, we'll talk about the problem of scheduling a little bit, then we'll go ahead and talk about Nova filter schedule concepts, and then we'll deep dive into overt scheduling, giving a lot of samples. I think the best way to understand stuff through samples. Okay, can you raise your hand if you heard about overt? Yeah, I guess a lot of you are. It's a home crowd. So overt, for those of you who don't know what is overt, overt is a management platform for VMs based on KVM hypervisors. Can handle thousands of VMs, has live snapshot, live storage migration, live VM migration, live, everything is live basically. And we support also advanced network configuration for those hosts and a lot of storage connections, SUN, NFS, cluster, etc. Basically, let's see what we've got. A long time ago, we got the questions from the users list. I urge you to use that list if you have any questions about overt. It's quite, it's quite active. How can I define a maximum number of running VMs per host? It's pretty trivial, but we didn't support that yet then. So we get back to it later. I just wanted to say that you should use the users list. Okay, what we had in overt a long time ago, basically we had two distribution algorithms for running and migrating VMs. When we selected a VM, when we ran a VM, then we selected a host based on CPU load policies, either even distribution CPU load or power saving, and then it's pretty, limited. We have only two distribution algorithms, and we can't construct a user-defined one. Basically, that is it. Then we take a look. We looked at the Nova scheduler, which brought us filters and weights. Very simple and easy way to filter to schedule VM on hosts. Basically, the filters are very cut and clear logic that gets a set of hosts on the left-hand side. Then we run a filter on them. Then we apply weights on top of them. Another cool slide from Nova Scheduler. We collect a set of weights, then we sum them up, and then we order the host that we got. Let's see a simple sample for Nova Scheduler. This is a RAM filter written in Python. Basically, it's a very simple method that gets a single host data and a set of properties, and then run a really simple code that either decides if this host is in the scheduling process or excluding it from the scheduling process according to the requested RAM for that VM. Okay. When we looked at that and took it to the data center virtualization, which is overt, we saw that we have a little bit of problem with that concept, because in Nova, each filter and weight is applied on a single host, and we have a larger concept of clustering in overt, which is called migration domain. So in the migration domain, each VM on a host can be migrated to a separate host on that migration domain, that cluster, And we have another concept of load balancing for that cluster. And also a policy container, which a user can decide and create its own policy and apply that on that cluster. So let's take a look what we had in Overt. Basically, we can create internal and external filter and weights. The internal part is used for better performance. We are within the server, so we get a quick access to the DB. And originally, all the filter and weights from the previous Overt back then, when we didn't have filters and weight, were migrated into that internal scheduler. And the external that basically all the users can support and extend. We apply all the filters, we apply the filter and weights on all the hosts in the cluster for better performance, and we want to have a better grasp of how the cluster behaves. We have containers we call cluster policies. For each cluster, we can define the set of filters, set of weights, and a single load balancing per each cluster. And then we support custom properties that you can, it's kind of pass-through to the filter and weight. This is a diagram of the new model. On the left-hand side, we can see a set of hosts within the cluster. Then we apply each filter, chaining each filter one on top of the other. And then we construct a weight table, which gets us the result of the selected host that we want to schedule the VM on. We had the same concept as Nova and filters. The existing logic that we had previously, which were basically validation, was migrated into internal filters, and we can extend it using in Python using the external scheduler that I will get into later. I want to show you a really easy sample of how we can use filters. Basically, this is a filter in Python. The name of the class will be the name that the server gets. The properties validation are basically a set of property that you can add within the server, and then the filter will get it. This is the name of the filter, and this is actually the signature that you need to override in order to extend a filter, to add a filter to the system. This is how you get the custom properties from within the filter. Basically, I didn't tell you what the filter is all about, but here you can see we get the time, and if the time is within the interval that we get from the user, then we print we print the host. We return all the hosts that we got. If not, we just exclude all the hosts from the filter. That's kind of a bank example. Okay. Let's talk about the weights. It weights all the hosts that pass through the filters. We have the predefined weights. That the first two are CPU load filters, and then in 3.4 we added a lot more weight models. I said filters. Weight models, which is kind of easy now to add because we have the new architecture. Each filter can have factors. We can prioritize the filters. Each weight can have factors. We can prioritize the weights using factors. We can also add external weights. Let's see another sample. In this sample, we use a connection to the server using Python SDK that we have. This SDK is backward compatible and stable. We connect to the SDK, and then the logic of the wait is basically we iterate over all the hosts, and we append to a list a tuple of the host ID and the weight of that host. Here it's a little bit cut, but the weight of the host is the number of active VMs on that host. So if we have a host with, basically it will be ordered by a number of running VMs within that host. Let's continue. Talk about the load balancing. That's the third model we have in the cluster policy. Each cluster policy can have only one load balancing logic. Basically, you can do whatever you want within the load balancing, connect to the SDK, and you can shut down everything, basically. But what we support internally is that the load balancing logic will return a VM and a set of hosts. I will show it in a sample later on. And we will migrate that VM, a single VM within the server. It's basically more safe to migrate a single VM within, a period of time, not to cause a migration rush and, use all our resources for that. It's pretty not safe to do that. You also have a pretty fine load balancing within overt. The two legacy ones on CPU, and now added in 3.4, even distribution one even VM distribution that we didn't have. The same balancing sample that I want to show, as I showed earlier, is we get the same numbers that we want to shut down all the VMs, but in this example, we will actually do that and not exclude those that prevent users from running host VMs like in the filter example. Here we will show how in that hour, in the wake-up hour, we will basically get all the hosts, and if it's wake-up hour, we will activate all the hosts. If we need to sleep, and then we will connect using our SDK and get all the VMs from that host. We will stop all the VMs and we'll deactivate the host. Same bank example. This is how we use it internally to migrate VMs. You get, according to some logic, you get the overloaded host. It's a code snippet. Then you select, here it's random, the first VM on that host. Then we actually print it because we're using stdio to get the data from the module, and we return it, and we return a right listed host, which is kind of a filter. The first filtering we do before we activate the filter and weights and the normal process that we do. Basically, as I said, we have a cluster policy, which is a container for all the filters and weights and a single loading balancing logic. And we have two optimizations for a cluster policy, speed and overbooking. Basically, we run each time we schedule a VM, we run it one by one because we want to prevent overbooking. We want to guarantee the same resources for each VM. If we will try to schedule two VMs together, we can fail because they both see the same resources. So basically, the speed optimization is to exclude the way of the hosts. So later on, the load balancing will do the weighing for us and balance out the cluster for us. And the overbooking is to emit the, I don't know, just be able to paralyze the scheduling process. Let's see if we can show those pictures within Overt. Okay. No. Okay, this is Overt. The VM is, because of Wi-Fi and VPN, the VM is unknown. It's running somewhere. Okay. Here I configure, that's it. Here I can configure a new cluster policy. Can give it a name, like the shutdown one. I can add the external filter that I've added to the system, the shutdown host filter, to the enabled filters. As a weight, I will give optimal for power saving. That's try to aggregate all the VMs within a single host as much as possible. Then I will select the balancer that I created earlier. I can give it wake up hour like 8 a.m. and shut down hour at 8. Press OK. Should be created. Okay, I don't know what happened. Second. What? Okay, let's go back to the...
It takes some time, actually.
No, it shouldn't take some time. What? Yeah, I'm not connected to the VPN.
It talks about some time.
No, something happened to the VPN. Doesn't like me. Yeah, I have screenshots, but maybe it will work. Second. Okay, let's take a look at the screen. It works, believe me. Okay, we were here. Wait a second. I'm connecting. No, still no. Never mind. I will show you that one. Then you go to cluster. No, still not working. Okay, forget about it. Okay, I create the cluster policy that I've showed you. Then I created to a cluster that I already defined, so all the hosts within that cluster will act according to that cluster policy. Okay, let's talk about how it's implemented in the back. It's disabled by default. Whoever wants to extend, to add filters should be able to know how to install the external scheduler. The external scheduler is a separate process written in Python. We externalize it because we want to guarantee the engine safetiness. If a user writes a code, it can be dangerous to the system. We want to allow other languages as well. If you know, the overton is written in Java. So, and this model is written in Python. And going forward, we want to support SAS, which is kind of a scheduling as a service. Yeah, that's right. Oh, wow, yeah. It's a separate RPM. You need to manually install it. How it works, basically it's initialized. It reads from a local directory all the filters, weights, and balancing logic that you wrote. Then it's published in an internal API. The engine, the server, reads it, and then it waits for calls from the engine for filtering, weighing, and balancing. This is how it looks like when it's loaded, the filter and load balancing here. Okay, back to the users list. Now we can easily write a filter that maximize the number of running VMs per host. Okay, pretty early. Okay, to sum it up, we support easy Python plugins for you to use for VM scheduling. You can manage a separate policy per each cluster, for each group of hosts, and every version that comes out for Overt gets new modules for scheduling. Questions? Yes.
So the question is that I have the possibility to read from what the hypervisor provides, memory utilization, CPU utilization.
Yeah.
Since you have a Python extensive API, if I got it right,
Yeah.
you may have the possibility to know if the storage behind or the storage framework behind is constrained. So you have the possibility to say, all right, do a storage migration, these virtual machines to the other storage, which is SSD based or whatever.
Yeah.
So you just need, for example, to have a good talk with all the storage big guys and find more things about their IOPS and what we are doing on their storage.
Yeah.
To get that information, right?
Basically,
Yeah, because we have the memory, we have the CPU, maybe we have some network information about throughputs and stuff.
Yeah.
So what's left behind is the IOPS and the quality of the storage.
you can think of whatever, you know. You all heard a question? I think so. Yeah. I think within, you know, when you extend. Okay. You can do whatever you want when you extend, you know, a filter, or when you basically can connect to every provider or use any SDK that you like. So what we provide within the engine is all that you ask, you know, memory and CPU load, and if you want to connect to other external provider, that it's your own choice. Did I answer?
Hi. So we had a few guys in the Overt workshop in Bangalore, and they were asking us to connect the scheduler to a BMC system that is monitoring extra parameters. For example, they can monitor the CPU temperature and the fan speed, and they can actually predict that if the fan speed is constant or 0 and the CPU temperature is high, that host is going to crash and burn in a few minutes. So what they asked from us is to give them a list of hosts, and they can actually blacklist some of them because they are aware of more information than what Overt should have. And there are so many other examples which are very similar. For example, Cisco has very similar concepts. They actually want to blacklist some of the hosts because the networking is going to go down there. There are a lot of very similar scenarios in very big enterprises. This is actually highly wanted.
Absolutely, sounds promising.
Yeah. So now you have the power, you can actually do it yourself.
Well, my first immediate simple question was, all right, I know about my CPU, my memory. Maybe I know about my networking because we do the networking. So the next good thing is if I had the storage I/O information or information that had to do with the quality of my storage, perhaps I could utilize multi-tiering in a storage or store, as we mentioned, a virtual machine from one place to the other. That could be nice with this engine.
So there are endless use cases of this. That's all. Hopefully the infrastructure, so everyone can actually implement his own use case without the need to modify all over for that. So sometimes some organizations have to provide a network, we can't really do this.
More questions? I think we are done early. Go drink a beer. Thank you.
Thank you.
מה שאמרת לי, הייתי לך, לא לחשוב על זה.